So in yesterday's lecture, what happened? In yesterday's lecture, we did this D'Alembert's formula for the solution to the wave equation, and okay, I'm sorry I have not printed adequate number of copies. I just printed 10. But there's one more here. You can just pass it up. So you click on this. Anyway, so in the wave equation, like the heat equation, there is this time variable, right? So the t variable is corresponding to the time variable, and it's a natural thing to ask what happens to this function, which is the solution to this wave equation, when you let t go to infinity. When you wait for long enough, what happens to the solutions to the wave equation? Okay, so that's what we will try to understand in the very beginning. That's the large time behavior. Okay, so this is the theorem, and in fact the statement of the theorem says something very profound, and you can actually arrive at that result by simply using the D'Alembert's formula that we derived yesterday. Okay? So it goes as follows. Okay, suppose you take your wave equation, okay, and you feed it initial data u0 and u1. This is the initial value problem for the wave equation, and there's a solution to this problem. And by now we know what is the solution to this problem. You can write it in terms of u0 and u1 and this constant c, right? There is that average term, and then there is the integral term. So we will, that's the D'Alembert's formula. So we are going to make this assumption that both this u0 and u1 are compactly supported. This is the standard assumption that we have been making, that both these functions are 0 outside an interval. So suppose this is the real line, and let us take an interval AB. Okay? A. So by functions having compact support, we essentially mean that if you plot these functions u0 and u1 on this plane, outside this interval AB, your function is 0. Okay? So it's non-trivial behavior, if at all it has any. It is happening only inside this one. So that's what we are assuming about the two functions which are going as input for this initial value problem. And the claim is this: the solution to the wave equation is a function of two variables, x and t. Okay? The claim is, okay, you fix any x in R, and now you look at this solution u of x comma t. Okay? Once you fix one of the variables, whatever you get is just a function of the t variable now. Okay? Because you have fixed the x variable. So the statement of this theorem is that if you let t become larger and larger, that function of the t variable, because you have fixed x here, it goes to this guy, and that is a constant because you have simply integrated that function u1 on the interval AB, okay, and then divided by 2c. So this is the claim, that the solution to the wave equation at any point x, if you wait for long enough, it becomes a constant. Okay? Now, let's try to prove this result. See, this does not, yesterday we had shown one picture that if initially if your data has got compact support here, at a given time capital T, your solution will also have compact support. We said that that is the finite speed of propagation property. that it will be 0 outside that and it's non-trivial only. The point that we are emphasizing here is that it's t going to infinity. Because you see, at every time slice, it was having compact support, but you are anyway letting t go to infinity. In the t going to infinity, the fellow that you get, whatever that candidate is, it does not have any compact support anymore because it is equal to the same constant everywhere. So that's the point we are trying to make. Okay? So let's try to prove this statement, and it just fits this slide. There is nothing great in proof actually. So we are given a function of two variables, u of x comma t. The statement said that, okay, you fix this variable, the spatial variable x, and then you let t go to infinity in this function. So let's fix an arbitrary x, okay? And as I claimed, this whole thing is just a consequence of the D'Alembert formula. So the solution to the wave equation, given u0 and u1, we know how it looks like. It is exactly this formula, okay? So it's the average of u0 at these 2 points, x minus ct and x plus ct, and the integral of u1 on the interval x minus ct to x plus ct, okay? Now, we have fixed that point x, so we have only got to play with the variable t, okay? The claim is this: because I have fixed the point x, I can always, corresponding to that point x, I can pick a t large enough such that these two quantities, x minus ct, will go to the left of a. Like x is picked somewhere, okay? Suppose this is your point x, okay? So I can pick a t large enough such that I can move it back by some amount so that it goes past this interval, so that this fellow is x minus ct. This I can do for any x that you give me, okay? Depending on the magnitude of x, your t will vary because c is also fixed. Similarly, the same t will also do this job. X plus ct will be bigger than b, okay? You see, in this case, in order to go beyond b, you need not add anything to it. Suppose the point were here, and then whatever we are doing by moving it to the left of a, we will do it to the right of b. Essentially, we are saying that, okay, the maximum t that will do the job for these two jobs, you just pick that for a given point x, and that will make sure that these two things happen. Why are we wanting this to happen? Because this is where u0 is evaluated. u0 is evaluated at x minus ct and x plus ct. And if we make sure that these two guys are outside the interval AB, essentially the contribution of u0 is gone, because u0 has compact support in AB only. Outside AB it is 0, so it doesn't matter, its contribution is gone, and only thing that matters is this. But if you have got this interval, let's say, this is x minus ct, sorry, and this is x plus ct, let's say, okay? Now, you have got this interval x minus ct and x plus ct in which you are integrating u1. But if your u1 is non-zero only in this interval, that integral is essentially integral from a to b. Okay? So that's the only observation here. Okay? For any fixed x, you can pick a t large enough such that these two things happen. And hence, if we go back to the D'Alembert's formula, you get that u of x comma t, the u0 terms are gone anyway, and you get this. And because this is a larger interval which contains AB where u1 is non-trivial, this integral is essentially this integral. And the 1 upon 2c is just a constant, it goes with it. Okay? And that is what we said. And you see, for any point x, you can find a t large enough such that this happens. And for any t larger than that t, the same constant keeps happening. Nothing changes. Because if you have found a t which did the job for you, any time which is larger than this little t will keep doing the same job for you. So if you are standing at a point x, your solution to the wave equation will become constant eventually. So that's the whole point of this theorem. I hope this is clear. And this little observation, you see, it's just a consequence of this formula, and then this little thing about, whether you can shift points around on a real line. Okay, that's it, and that is the proof of the last time behavior for the wave equation. Okay. Now I would like to talk about something known as the characteristic parallelogram. Okay, it's a very interesting concept, and it can be used to assign values to a function such that it solves the wave equation. You need not do anything if we understand what is the characteristic parallelogram. Okay, so let me just try to sell this point that I just made. So characteristic parallelogram, so if you are given a wave equation, this is our standard wave equation that we have been seeing for the past 2 days, utt is equal to c square ux. Corresponding to this equation, we say that a parallelogram on the xt plane is the characteristic parallelogram. See, we all remember from school days, right? Parallelogram, it has got 4 sides and 2 sides are parallel to each other. Okay, that's the parallelogram. So now, if you have got 4 sides to your parallelogram on the xt plane, if 2 of its sides are parallel to this line, x is equal to ct, and the other 2 are parallel to x is equal to minus ct, you call such a parallelogram as the characteristic parallelogram associated with this equation. Okay? So let me just draw the picture so that we get the hang of it. So this is the xt plane, let's say. Okay. Now, you draw these lines. Suppose this is the x is equal to ct line. Okay? It looks like c is equal to 1, but don't worry. Then you draw one more line, which is the x is equal to minus ct line. So that will be, of course, perpendicular to this line. So this is x is equal to minus ct. So you got these 2 lines. Now, if somebody asks you to draw a characteristic parallelogram associated with this equation, see, the point that matters is the constant c which is in the equation. Okay? So what you do is, you draw 2 lines. Your parallelogram should have this property. For example, this fellow. See, these 2 sides of your parallelogram are parallel to x is equal to ct, and I'll draw other 2. These 2 are parallel to this line, x is equal to minus ct. So now, according to this definition, I can call this a characteristic parallelogram associated with the equation utt is equal to c square uxx. Okay? So, there can be infinitely many characteristic parallelograms. Okay? So, the way I have written it looks like it's a square, but it need not be. It can be anything. Okay? For example, I draw one here. It need not be always here. So, see, this is parallel to this red line, and this fellow. So that's a characteristic parallelogram. So only stipulation is that you got 2 sides which are parallel to x is equal to ct, and the other 2 sides which are parallel to x is equal to minus ct. Okay? So that's the only stipulation. If you have got a parallelogram in the xt plane which satisfies that, you call such a parallelogram as the characteristic parallelogram. Okay? There is value for introducing this concept. Okay, so and I think we have drawn a picture here. You got and every parallelogram will have 4 vertices. We call those vertices A, B, C, and D. Okay? So this is the xt plane, and you have got that. Now, let's try to. So here I just want to do this exercise with from our knowledge from class 12. Okay? So what are we doing here? In this column, we write down all the coordinates of this 4 coordinates of your characteristic parallelogram in the xt plane. And yesterday we introduced this new psi eta plane, right? If you give me a point xt, psi was x minus ct and eta was x plus ct. So if somebody gives you this point, you can just blindly write down what is psi and eta. So that's what we have done in that column. Okay. So let us try to understand how we got here, this particular table. Okay. So you got x, you got t. Now, maybe I have mistaken with the slopes here. Yeah, it looks like that, but I will. Yeah, by the way I have written, no, t is here, x is here. But it doesn't matter actually for what we are doing. So let's start with this point A. Okay, A. I am saying that x has, A has got two coordinates, x naught. If I move that there, no? Okay. Sorry guys, I think I have just, see what, I realize what I have done. See, when I say this is a line of slope x is equal to ct, right? So t is here, x is there, and the slope is c. But in fact, I have written everything for t is equal to cx. Okay, t is equal to cx. That's what I have done. So we will just think of wherever you see c in the slide. I will change that later on. You think of it as kappa, and kappa is 1 upon c. Okay? Because if you have got x is equal to ct line, this is the same as writing t is equal to 1 upon c times x. Okay? And I am calling 1 upon c as kappa. Okay. So I am extremely sorry about this. I missed this thing. But I will try to explain the thing here. I will go back to x here and t here. So A, I will take coordinates to be x naught, t naught. Forget what you are seeing there. So I will just explain it here. So this has got the time coordinate to be t naught. Okay. Now I want to pick some point here, B, which has got a coordinate which is t naught plus tau 1, I think I have called that. T naught plus tau 1. Now, if I have to draw a line here which has got a slope which is equal to 1 upon k, okay, or k kappa, and it has to have the y coordinate which is equal to t naught plus tau, okay. So how much I have to go on this direction? So that's what I'm saying. So here, if I got slope kappa, it will be x naught plus c tau 1. See, I have gone by that much amount, x naught plus c tau 1, and then I have added t naught plus tau 1 here. So that's what goes here. So this is b. Okay. So that's the coordinate of this x coordinate here if you have got a slope c here. And for the moment you just think of this as line with slope c and you are taking that. And then you start at this point and then you introduce two more points here. This is t naught plus, this is the other point, tau 1, tau 2 here, and this is t naught plus tau 1 plus tau. Okay. So if you want to arrive here at some point c, this fellow we are saying it should have slope minus c. So if you are starting here and if you are going by a slope of minus c, this fellow will have an x coordinate which is equal to x naught plus c tau 1 minus c tau 2, because you start here with x naught plus c tau 1 and you are going by slope minus c. So you go by that amount, because here you are already at t naught plus tau 1 and this length is tau 2. This length is tau 2. So you go, this is the thing, and this is t naught plus tau 1 plus tau 2. Okay. And then from here you draw another line of slope c now, and you reach until here and you call it d. And that fellow, because you are, see, this is the same as drawing a line of slope minus c starting at this point. So this will have x naught minus c tau 2, because that's the amount you are going, and then the y coordinate will be t naught plus tau. Okay. So what we are doing is we are starting at this point and we are drawing lines of slope c here, slope minus c here, slopes minus c here, and slope c here, and you get those 4 points, and these are the corresponding coordinates that you get in the xt plane. Okay. Now once you have got your coordinates in the xt plane, you blindly write down, if you take this point x comma t, we have defined what is psi eta, and psi eta is x minus ct and x plus ct. Okay. So if you are given xt, your psi is just x minus ct. So now you have got x naught t naught, this psi is x naught minus ct naught, and this is x naught plus ct naught. Similarly, this is your x coordinate, this is your t coordinate. You just write this minus c times this, which is here, and this plus c times this, which is here. So you just do this exercise for the 4 set of points that you have. Okay, there's a value for doing this. Okay. The one important thing to notice here is that, you see this fellow, it has got the same x coordinate, these two. And these two have got the same, so that's the thing. If you observe here carefully, maybe in the next slide I have slightly simplified this and I will show that here. So we are going to call this heavy notation of x naught minus ct naught as psi naught, and x naught plus ct naught as eta naught. Okay, so that the point corresponding to A, okay, let me rub this, in the psi eta plane, your A gets mapped to psi naught eta naught, right? So psi naught eta naught, let me call that point here, psi naught eta naught in the psi eta plane. Now what is this fellow? The B map gets mapped to, this is A, which is psi naught eta naught, and B gets mapped to, this is psi naught again, and this is eta naught plus something. Okay. So because your psi naught has not moved, so B comes here, this is psi naught, this is eta naught plus something, which is 2c tau 1. That is the B which gets mapped. Now you come to C here, this is psi naught minus 2c tau 2. So C here, this is, because it's to the left of that, minus c 2c tau 2 comma, and what is this one? This is eta naught plus 2c tau 1. So you are actually here, sorry. So C is here. So psi naught minus 2c tau 1, tau 2 comma eta naught plus 2c tau 1, and this point D, now we know that it is this times eta naught. Okay. So the thing to notice here is that the characteristic parallelograms in the xt plane gets mapped to a rectangle in the psi eta plane, because these two fellows, they have got the same eta naught, eta coordinate. These two guys have got the same psi coordinate, and these two guys have got the same psi coordinate. So this, if you take characteristic parallelogram in the xt plane, okay, where the sides are parallel to this x is equal to ct and x is equal to minus ct. The coordinates in the psi eta plane are such that they get mapped to a rectangle. Okay, so now we also proved something yesterday while proving the D'Alembert's result, that u of x comma t, the general solution to the wave equation, will look like some function p, because we don't have any data yet. It is x minus ct plus some function q of x plus ct. That means p evaluated at psi and q evaluated at eta. So if you have got an xt point, the corresponding psi eta points is where you will evaluate p and q for the general solution. So for the first point, the point A, the value of u at the point A is simply p evaluated at psi naught and q evaluated at eta naught. I mean, you don't care what p and q are, but for some functions p and q. And similarly, for this point B, you see, this is still psi naught. Then the second coordinate is eta naught plus 2 theta 1. So q evaluated at this. Similarly, for the value of u at the point C is this, and value of u at the point D is this. Okay. You must be wondering why we are doing all of this. It's because of this little observation here. Okay. What is that observation? It's here. You see? If you take the value of u at the point A and you take the value of u at the point C, you just look at their right hand sides here. If I sum this fellow and this fellow, and if I sum the value of u at B and u at D, you get the same exact value. Once P and Q are fixed, okay, because you are thinking of a general solution for a given problem. Now, value of u at A plus value of u at C is the same as value of u at B and value of u at D. So where was this A, B, C and D? They were sitting here, right? They are the vertices of your characteristic parallelogram. So this little exercise of moving to the psi eta coordinates, okay, and writing down the general solution to the wave equation is essentially telling you that in the xt plane, somebody comes along and tells that, okay, you have got a solution to the wave equation here, and then you know that constant c in your wave equation, you write down any characteristic parallelogram associated with that wave equation. The value of the solution at the two opposite vertices, when you sum them, they are the same. Their sums are equal. So this is known as the parallelogram identity. Like you can write any characteristic parallelogram in the xt plane and you go to its vertices, you simply add the values of u at those two vertices, opposite vertices, they will match. The sum matches. And that's just a consequence of these four equalities which are written here, where you can just observe that when you sum u of A and u of C, you get the sum equal to u of B and u of D. Okay, so even though I struggled quite a bit to explain this, okay, so if not the way we arrived at, I want you to remember this particular property which is known as the parallelogram identity, and that's what we state here. Okay, so it says, okay, let A, B, C and D are the four vertices of any characteristic parallelogram associated with your wave equation in the xt plane. Any characteristic parallelogram you take in the xt plane, and you sum the values of your solution at the two opposite vertices, their sums are equal. Okay, this is known as the parallelogram identity. Okay, I hope this is clear. Okay, at least the end statement that you write any arbitrary characteristic parallelogram in your xt plane associated with your equation, you simply, then this holds. The value of u at the two opposite vertices, they sum to the same value. Okay, and this particular identity is very useful, and there are two problems in the problem sheet where you have to essentially do this parallelogram identity and solve and get the values of the functions, the solutions to the problem. Okay, So now let's, I hope this is clear, the parallelogram identity. Now we will get to the wave equation on an interval, because you guys have studied the heat equation on an interval. So you can also study wave equation on an interval. For now, until now we have always been studying where x is running in the real axis. But you can also restrict it to an interval in R. And the setting is as follows. You pick any interval AB. You ask for a function u which satisfies the wave equation in that interval. Okay. And of course, these are the two initial conditions that you have to impose for an initial value problem. Because you are posing the problem in a bounded interval, you have to assign what is the value of u at the two endpoints, like in your heat equation, and we are assigning that it vanishes at the boundary of your interval. Okay, so this is an initial boundary value problem, because you are assigning what is the value of u and its time derivative at time t is equal to 0, and also the value of u at the two endpoints. Now, in the heat equation setting, you guys actually derived an expression for the solution using the variable separable method. And there you came across this Fourier series and all that. We will consider that later on. For the wave equation also you can do a similar thing. But for now, we want to sell this idea that you can actually solve this problem using the D'Alembert formula and the parallelogram identity that we have just seen. Okay. See, the problem with D'Alembert's formula is, D'Alembert's formula says what? If you have got a solution to your wave equation, and if you want to write the value of that solution at a point x comma t, you need to know the data at x minus ct, x plus ct, in that interval, the entire interval unit. So suppose this is your axis, okay, where x lies, and this is your t-axis, and suppose this is my point x comma t. I want to know the value of my solution at this point, and if the point I'm trying to get at is, can we solve this problem just by D'Alembert's formula? Because we know that when this x runs in the whole of R, we can solve it by D'Alembert's formula. What if x is restricted to an interval? Can we still use D'Alembert's formula to solve this? So suppose this is my interval AB, okay, where I'm trying to solve the problem. I take this point x. Now, this x lies in the interval AB and I'm interested in that. So, I draw those lines. In order to do the D'Alembert's formula, you need to know what is x minus ct and what is x plus ct. So, this is the point x, right? And so this is x minus ct and this is x plus ct, let's say. This is the trouble with D'Alembert's formula if you try to apply it for a boundary value problem, because now you have got x plus ct and x minus ct sitting outside this interval AB. We do not know the values of u0 and u1 beyond that interval, because this is the given problem. Somebody comes along and tells that, okay, this is where I want to solve the wave equation, and only there I give you the value of the initial conditions. They will not tell us what is that initial condition beyond that interval, right? And it's not relevant also. So, if we blindly try to write down D'Alembert's formula in this setting, we will face this problem that we don't have access to u0 and u1 in this larger interval. And if you keep going up in the t-axis, that means you are trying to solve this problem for larger times, your x minus ct is even going farther and farther, and x plus ct is even going to the right. So there is that problem that you don't have access to the data there. It turns out that if you have got an interval AB like this, the best you can do is up to this time, which is a plus b upon 2. Okay, so I come here and I draw these lines. Suppose I take c is equal to 1. Okay, so This is the point which is a plus b upon 2 comma a plus b upon 2. Okay? So in this particular triangle, however, if I pick any point, I can draw the lines of slope 1 and minus 1. It will always fall here. And I can use the D'Alembert formula to find the solution to the wave equation in this entire triangle. In this triangle I can find. But not beyond that. Because any other point I pick, for example this point here, I draw the line of slope 1, I land here, there is trouble. Of course the line of slope minus 1 may land here, but we have nothing, no information about the data for this patch of that interval, and D'Alembert's formula will break down. So, see, whenever somebody gives an initial boundary value problem, you are actually looking to find the values of your solution in this entire cylinder, right? Like, just bear with me, this is supposed to be very parallel to the p-axis. You want to find the value of your u at every point in this cylinder. That's what it means when I write a comma b cross 0 infinity, where x comes from here and t comes from here. Right? You want to get that solution in this entire patch. Okay? Now, unfortunately, D'Alembert's formula will help you only for this triangle in that patch. Now, how are we going to solve the wave equation in this part of the domain? Okay, just depending on u0 and u1. So that's where this parallelogram identity will come in handy. Okay, so that's what we are saying. So we will try to explain it using pictures. So this is the point I tried to make earlier. So this is A, this is B, this is that midpoint a plus b upon 2, and this is in the time axis also, this is a plus b upon 2. So in this triangle, you pick any point in this triangle, we can write this D'Alembert's formula, and we can get the value of your solution at this point, at any point in this blue triangle. Okay. Now, I claim that you can use triangle identity, this parallelogram identity, to solve for the rest of this domain, that cylinder. And how does it go? So, yeah, so there is this red triangle there. So what are we doing here? So this fellow is the line of slope minus 1, right? So you have got this line parallel to the t-axis, which is going starting from a comma 0 here. You continue this line until it hits that line. Okay? So you get this triangle here. So that's the red triangle that we are saying there. Now, you see, by D'Alembert's formula, we have got the values in this full triangle, in the interior of the triangle and also on the boundary of the triangle. Now, let's draw a characteristic parallelogram associated with this equation in that red triangle. Okay? Pick any point. Suppose this is where I want to assign the value of u at this point in this red triangle. What I do is, I draw a line of slope minus 1, it hits here. I stop there. Then starting here, I draw a line of slope 1, it hits here. Whenever it hits the boundaries, I stop. And here I draw again a line of slope minus 1, it hits here. And this is line of slope 1 again. So this blue patch, it's a characteristic parallelogram now. It satisfies this condition that its sides are parallel to lines of slope 1 and minus 1. Okay? Now, what did the parallelogram identity say? The value here plus the value here is the same as the value here and the value here. See, out of these 4 points, we know the value of u at 3 points now. Because on this boundary here, on here, we know the values at these 2 points thanks to D'Alembert's law, D'Alembert's formula. We have found the values at these 2 points. And here it is assigned. We are told that it is 0 for, see, this is the condition we have imposed, like u of a comma t is 0 for all t. So it is 0 here. So this value is known, this value is known, this value is known, so you can find this value. And there is nothing special about this particular point here. You pick any point in this triangle, you can do this game. Suppose I take this point, I draw the line of slope -1. It hits this triangular thing. Then I draw a line of slope 1. Then I draw a line of slope -1. Essentially I get another parallelogram, characteristic parallelogram, where the three vertices I know the value of u. And I am just looking to find the value of u at the fourth vertex. You can do that. Okay? So this is how you can solve for every point u in this red triangle. And there is nothing special about the red triangle here, where we extended this line of slope -1 and we went there. We can also extend the slope of a line of slope 1 to this side also until it hits this axis, x is equal to b. So now you get this brown triangle here. Here again you can do the same game. Pick a point, you construct those parallelograms. Because you know the value of u along this axis, that is 0 again. U of b comma 0, b of t is 0. And you know the value of u on this boundary thanks to D'Alembert's formula. So you pick any point, you draw those parallelograms. Okay? Where you will always have 3 points where you know the value of u, and you will assign the value of u for the fourth one. So this way you can solve in this brown triangle also. Now, it looks like, okay, maybe this is where it stops, but you can actually continue doing this. So what we do is, okay, we start at this point, we draw the lines of slope -1, and from here we draw the line of slope 1. So we get this, what did I do? Oh, yeah. So we get this parallelogram again. Okay. So here, you pick any point, you make that parallelogram. Okay. This point will always be a vertex for the parallelograms that you draw here. For the characteristic parallelograms that you draw, this is always a common vertex, and there you know the values, okay, by D'Alembert's formula. So you can assign values for you at any point in this also, in this pink region, again by parallelogram identity. You have to essentially draw those characteristic parallelograms. And then once you have done that, you continue this line, because you see now it's just repeating what you did earlier. So first you solve here, then you solve here, and then you keep proceeding. Okay, and this how you can fill this entire cylinder. Okay, so this has a drawback, of course, that you cannot write down. I mean, some people do try to write down explicit formulas using these characteristics and all that. But I hope you get the picture how it is done. Like, suppose there is a point x. So I tell you that, okay, find the value of the solution to this wave equation, the boundary value problem, at x is equal to a plus b by 2 and t is equal to 100. What you do is you keep doing this sequentially until you get a region where t is equal to 100 actually comes. And then you just draw the characteristic parallelogram at that point and you are done. So this is what we are after. Okay, so this method of a Fourier series is not the only way to solve the wave equation, the boundary value problem, initial boundary value problem for the wave equation. You can actually use the D'Alembert's formula followed by a sequence of parallelogram, identities to find the values of the solutions to the wave equation. So I hope this is clear. Okay, so this is very geometric. You just keep drawing those characteristic parallelograms and you get there. Okay. Now we want to just revisit the heat equation on an interval that you guys have studied. Okay, and a series. Okay. So this is the initial value problem for the heat equation, because you see there is a ut here, not utt. And also for the initial value problem for the heat equation, there is only one input, which is the value of u at time t is equal to 0. And you are 0L is your interval where you are trying to solve, so you are fixing the value of u to be 0. Okay. There is no need to fix these values to be 0. You can assign anything that you like. You can assign also functions. You see, when I have fixed the point x is equal to 0 here, what is left is a function of t. You can also assign the, you can give data as some functions of t also. And you can try to solve them. That's just, adding additional difficulty. Otherwise, the principle is one and the same. So, and this you guys have derived. You showed that by variable separable approach. By that we mean the following. See, we are trying to find a function of two variables, u of x comma t. Okay, and we are convinced that this fellow has got a unique solution. Okay, suppose somebody comes along and tells that for a given u0 there is a unique solution to this problem, and then we go ahead and assume that, okay, I will write this function of two variables as function which has this particular structure. There is some kind of variable separable structure, like it's a function of t times a function of x. And then I manage to find those functions a and b. Then, if there is only one solution to that problem, and if we manage to find these functions which solve that, then this is the guy. Okay. So there is no need to look down upon the method of separation of variables. You see, anything works. Like you are after a function which solves the given differential equation and satisfies the data. It doesn't matter which method you take, as long as you justify whatever you have done eventually. And so this is the solution, where what are these coefficients alpha n? They are related to what this guy u0 is. Okay. They come as the coefficients of this series, sum that you have, the Fourier series for u0. Okay, the sine series, the coefficients for alpha. Okay, so this is the gist of what happens when you try to solve the heat equation on an interval using the Fourier series. Okay, so we will take cues from this and we will try to adapt similar strategy to solve the wave equation on an interval. Okay, so this is the wave equation. Again, it's exact similar setting as we were doing when we were trying to use this D'Alembert's formula and the parallelogram identity. So you get this. So there are two data here, u0 and u1. So let's start with this. Suppose that, okay, the solution has this particular structure. It's a of t times b of x. Then, because u of 0 comma t and u of l comma t should be 0, because we have this boundary condition, that means a of t times b of 0 should be 0 and a of t times b of l should be 0. Okay, so when you have got product of two guys equals to 0, one of them should at least vanish. And because it's a of t and you are trying to find a non-trivial solution to this problem, that kind of forces you to take b of 0 and b of l to be 0. Okay? Because this particular last line, no, if we blindly take the solution, the function to be having this particular structure, that last line, u of 0 comma t is equal to 0, translates to a of t times b of 0 is 0. Okay, and this should be true for every time t. So this better not be 0, and you are asking for b of 0, because if a of t is 0 all the time, then you are not finding anything, because this is in the variable separable structure, u will become identically 0. So that kind of forces you to take b of 0 to be 0, and similarly that forces b of l to be 0. So we are assuming that we have got this structure for u, and this boundary condition forces us to take that this function in the x variable should vanish at the two endpoints. Okay. Then, okay, something happened. Oh, yeah. Now, when you plug it in the equation, there's something happening as soon as I approach that. So when you plug this particular structure in the equation, you see the left hand side, it has got only derivatives with respect to time. and the right hand side has got derivatives with respect to x. So when you, okay, a of t times b of x, when I differentiate it twice, I simply get a t times bx, because this derivation does not see b. Okay, and on the right hand side, similarly, that derivation in x does not see a. So a of t times bx. Okay, and then you are dividing by ab, and this is just rearranging, you get this. Because this fellow is just a function of the t variable, and this fellow is just a function of the x variable, and we are equating two separate functions which are functions of two independent variables, then they must be equal to some constant kappa. So that's the first observation. And the question you ask is what that constant kappa be? What that constant kappa can be? Okay, can it be any constant or some particular constant? That's what we are after. Okay, we are going by first principles. We are not plugging any particular expansion. We are supposing that okay, there is a variable separable structure, and we are trying to see if this particular form can be a solution to this problem. What are the obvious things that needs to be true? And this is first thing, that these two ratios should be equal to some constant. Now we try to answer what that constant can be. Okay, can that constant be 0, we ask. Okay, so one of those ratios is this, and if it is equal to 0, see, then you can throw this b of x to the other side. You are essentially saying that b double prime is equal to 0. And the general solution to this equation, y double prime of x. So here we need to recall some things from our ODE days. So if I have got y double prime of x is equal to 0, the general solution to this problem is y of x is equal to cx plus d. Okay, just trust me on this. Huh? So that's, you just integrate twice. So y of x is equal to cx plus d. Now, so b of x should have this particular structure, but b also satisfies this other condition, the boundary condition, that b of 0 is 0 and b of L is also 0. And when I take b of 0 is equal to 0 here, that forces d to be 0. And when I take b of L to be 0, that forces c to be 0. So essentially you get a 0 function. And you are trying to avoid that. You are trying to avoid trivial functions. So this tells you that your constant kappa cannot be 0. So those ratios that you had above earlier, we can deduce that they both should be equal to kappa, but they cannot be equal to any arbitrary constant. For example, they cannot be equal to 0, because then you will get only trivial solution for b. Okay? Yeah. So kappa is equal to 0 is not allowed. Now then you ask the obvious question, can this constant kappa be positive? Okay? Now, when I take kappa to be positive, again you take the same differential equation. Somehow we are not worried about what happens with a. We will worry about that later. Yes?
Can we take kappa complex also?
No. You may be able to, but as I told you, I never take complex things. Okay? Because we are taking a and b to be real valued functions. Okay? And there is that ratio, right? That ratio cannot suddenly become complex. We are asking only for real valued functions here.
Okay, sir.
Yeah.
Thank you, sir.
Yeah. So here you take kappa to be positive, and that translates to this equation. So it's y double prime minus kappa times y is equal to 0. Okay. And this is in the very familiar structure where we teach the ODE classes. And you can write down the general solution here also. Okay? The general solution will look like this. It's just a linear combination of e to the square root of kappa times x and e to the minus square root of kappa times x. Because the characteristic equation that you get is lambda square is equal to kappa. Okay? From here. And that's why the roots are square root of kappa and minus square root of kappa. You get this. So b of x is this. Again, these two boundary conditions make sure that the constants C1 and C2, they are both 0. Okay, because B of 0 should be 0. So when you take B of 0 to be equal to 0, that means you get C1 plus C2 is 0. Okay, so one is the negative of the other. Now you take B of L to be 0. Okay, that means E of square root of kappa times L, and C2 is minus C1, so you can just minus C1 times E to the minus square root of kappa times L. Okay, and because exponential never vanishes, the coefficient should vanish now. Okay, that means C1 will vanish. First you will show that C1 is negative of C2, and then you will show that C1 should be 0. Okay, so even when for any kappa positive that you pick, you will keep getting trivial solutions thanks to the boundary conditions. Okay, so this is also not good. So that ratio cannot be equal to a positive constant as well. So what's left then is negative constants. Okay, so now you take kappa to be negative. So that means you are trying to solve this differential equation, ODE again, where kappa is negative. Okay, and here, here you will get complex solutions because lambda square now is equal to kappa, which is negative. Okay, but because we are only looking for real valued solutions, you will get this linear combination involving sine and cosines. Okay, this is the general solution when you are looking for real valued solutions only. So you get this. So we are still not imposed, because there are these two hanging constants C1 and C2, we are still not imposed B of 0 and B of L to be 0. So when I take B of 0 to be 0, okay, this fellow will give me 1, so C1 should be 0. So this B of 0 equals to 0 forces C1 to be 0. Now that leaves this, okay, so we will, okay, C1 is 0. When I take B of L to be 0, you get this condition. Okay, now this is a product of two things being equal to 0. We can of course say, okay, let's say C2 to be 0, then we are going home because we are just saying that kappa negative is also not working. But thanks to the sine function here, there is hope. Because I can keep C2 to be non-trivial and make sure that this fellow vanishes. And we know where sine vanishes. Okay, so this equality forces us to take sine of square root of minus kappa times L to be equal to 0. And we know what should be the input here so that sine vanishes, that should be equal to n times pi. And that tells you that kappa should be minus n square pi square upon L square. And this is the reason why in the Fourier series when you wrote down, you got this n square pi square upon L square. Okay? Because only for these choices of kappa, you will be able to solve for B, which is a non-trivial function. For any other choice, you will get 0 solutions for B. Okay? Now, so these are the admissible constants, minus n square pi square upon L square, where n can be any integer. And the corresponding solutions are these. These were the solutions, right? The general solution to that ODE that we wrote down. Some constant times sine of n, my square root of minus kappa was there, and kappa is this. So minus kappa is just n square pi square upon L square. You are taking the square root, you get this. This is how you get those sine functions also. We are just doing everything by first principles and we get this function. Now we are going to disregard n is equal to 0. We will discard n is equal to 0 because this is true for any, when you take n between any integer, so we will take discard n is equal to 0 because there you will get again a trivial solution. Because when I take n is equal to 0, I get 0 again, so I'll discard that. And also we will discard negative integers because sine of n pi L upon x is minus sine of n pi L upon x. And we are just multiplying by a constant, and that constant can be taken care of by the C2. So we will just make sure that we are taking strictly positive integers here and the corresponding kappas. Okay? And that tells us that, okay, there were two ratios equal to kappa, and one ratio can be meaningful only when kappa is this. Kappa is minus n square pi square upon L square, where n is strictly positive integer, and the corresponding solution is this. Okay. Now, there was another ratio there also. So we will see whether we can solve that other problem corresponding to these kappas. So that brings an equation for A, and this fellow you can solve again. There is a general solution that you can write down, which is we just wrote down earlier, right? This is exactly the same thing. The linear combination of sine and cosine, but in the t variable now, because this is a differential equation in the t variable. So you get this. So we started off with this assumption that u of x has this particular structure, a of t times b of x, and we have got those expressions for a and b. We have said that b should look like some constant times sine n pi x upon L, and a should look like this linear combination of sine and cosine evaluated at n pi t upon L. Okay. So now we will just multiply them, because by the way we have built them, their product solves the wave equation now. Okay. But we have taken a leap of faith here in saying that, okay, if this fellow, okay, I skipped a couple of slides here. This, you fix a n, I take n is equal to 1, this will give me 1b, this will give me 1a, and I multiply them, and by the way we have done the calculation, that product solves the wave equation. I take n is equal to 2, in both these cases, I get a new function, and that also solves the wave equation. And yesterday we convinced ourselves that if you have got two functions which solves the wave equation, you take linear combination of them, that also solves the wave equation. And there is nothing special about 2, you can take finitely many and take the linear combination, and you will keep getting functions which solves the wave equation. But in the context of heat equation, Fourier took a leap of faith. He said, okay, I will not stop at finite combinations, I will take infinite combination of this, infinite linear combination of these functions. And that's what this is. See, you are taking the same. This is our a of t, this is our b of x for various values of n. And because any positive integer n is allowed, we are taking every possible positive integer n as an input and summing all of them. Okay? And we are thinking that, okay, maybe this will solve the wave equation as well. And it turns out that this also solves the wave equation. But you have to make sure that it satisfies those, of course this satisfies the boundary condition, right? Because boundary condition is in the x variable. When x is equal to 0, sine term vanishes. When x is equal to L, the sine term vanishes. So a sine term is sitting in each term, so that will vanish. And of course we are skipping one step of making sense of this infinite series. Okay, just trust me on this, that you can actually make sense of this. In the heat equation case, there was a e to the minus t upon something, right? And that enormously helps to show that the series is summable. Here, there is no e to the minus t. So we cannot blindly use similar strategy. This is a different strategy using, extending a given function by odd extension and writing down the Fourier series. It's a bit more involved, so that's why I'm skipping the step. Okay. So, but there are two more conditions which are involved. We are given what is the value of u when t is equal to 0, and what is the value of time derivative of u at time t is equal to 0. And that will help us decide what these coefficients a(n) and b(n) are. Because they are the coefficients of the sine series of u0 and the sine series of u1. Okay. So, the point that we are trying to make here is as long as your initial data, u0 and u1, have got a summable Fourier series, this method works. Okay. If you are told that, okay, these are the coefficients for u0 and these are the coefficients for u1, we can blindly build this function using a(n) and b(n), and that fellow will solve the wave equation with these things as the data. Okay? So that's the primer, this thing. And I believe I have run over time. Very much. Okay. In 5 minutes, okay, I will do Duhamel's principle. So Duhamel's principle, I have stated this principle before also when we were doing the transport equation. So Duhamel principle essentially is talking about if you have got an equation and if you have got a source term, how to deal with the source term. Okay? So now we are talking about wave equation, right? So suppose if there is a function f of two variables which is given, and that comes as a source term to your wave equation. For simplicity, we are taking the initial data to be 0. Okay? Initial data is taken to be 0 and you are taking some f here, some function. How are you going to solve this is the question. Okay? So there's a trick here, and that's the Duhamel's principle. It boils down to introducing a new function. Okay, what it does is, see here, this t, it is varying from tau to infinity. It's not varying in the interval 0 infinity. We are trying to solve this wave equation where little t runs from 0 to infinity. What this little trick does is, you fix a tau. So let me clear this. Okay. So this is our t-axis, right? T-axis. This is our x-axis. So this is the 0. T is equal to 0. Now, we are supposed to solve it starting from t is equal to 0. But in this approach, what it does is, okay, you take some tau which is strictly positive, okay, and now beyond tau, you try to define this function w, because this w is defined only for t's which are outside capital T, okay, which are beyond capital T, and this w is solving the wave equation, but with no source term here, okay, and when you treat this level, time slice t is equal to tau, as your initial thing now. Okay? Now, for an initial value problem for the wave equation, you need to impose two conditions, right? The initial condition at that time and also the derivative at that time. Now, the trick involved in Duhamel's principles for the wave equation is, for the displacement you give 0 only, for when t is equal to tau. But for the time derivative, that is the velocity, you assign the value of your source term, because this source term is a function of x and t variables both, so it will have a value when t is equal to tau, right? And that value you assign, because now when I fix t is equal to tau, this fellow will become a function of x variable. So that can go as a source term for the velocity here, the time derivative of w. And we know how to solve this, right? Because there is no source term here, there is an initial data. Only difference is that you are starting at tau. Tau is your starting point, but our methodology doesn't care what is the starting point. As long as there is an, on the x-axis, if you are given the data, for example, you can use the D'Alembert's formula to write down the solutions beyond tau, right? If I am given the value of u0 and u1 on this axis, I can use D'Alembert's formula to write down the solution at any point xt. Only thing I need to do is draw those lines and pick those points, and this is the interval that matters for writing down the solution to D'Alembert's by using D'Alembert's formula, and that's what we can do. So this is the trick in it. Now, suppose I solve this for every tau, okay? For example, I take tau is equal to 0.1, tau is equal to 0.2 and keep doing that, and I get a bunch of w's which are parameterized by tau. How is that going to help in finding u is the question, and this is the thing. What you do is, you define this function u to be integral of w in the tau variable. So the Duhamel's principle essentially tells you that if you want to solve the wave equation with f as a source term, you feed that source term as velocity at every time slice, and you solve separate wave equations. And all those solutions that you obtain, you simply integrate from 0 to whatever little t that you are interested in. And that fellow turns out to solve this equation. Okay? We will try to show that this is indeed the case, but this is the principle. This is known as the Duhamel's principle, which says it gives a recipe for finding solutions to the problem. Okay, where you have got a source term. The only thing that we have to keep in mind is we have to take time slices, and at every time slice we are solving a initial value problem for W. Okay, where the first initial condition is 0, the second initial condition is given by this F only. I hope this is clear, the strategy. Now, why is this fellow going to solve this problem? Okay, we have to show that. Why is this integral from 0 to t of W in the tau variable magically solves? Because when I integrate out the tau variable, the other two variables that are left are x and t. Somehow that function which is left out after integration magically solves this problem. Okay. Now, first observe that u of x comma 0 is 0, which is the case here, because when I take t is equal to 0, because there is nothing being integrated, so you get u of x comma 0 is 0. Now you differentiate that, because you have to first differentiate with respect to t and then take t is equal to 0. And now when I want to differentiate with respect to t, we know the Leibniz integral rule, because I am differentiating with respect to a variable which also sits as a terminal point. So yesterday we saw the Leibniz integral rule and we will use that. Okay. So this is the candidate for our solution. This is the claim that we made, that we are assuming that we are able to solve for W, and which we can using the D'Alembert formula. First observation is this, that u of x comma 0 is 0. Now let's differentiate this. See, when I differentiate this, first is W evaluated when tau is equal to t times the derivative of t. That's the Leibniz first term, Wxtt. Okay? And then you take the derivative inside. You get this. But Wxtt is 0. Right? Because if you go back, you see at the time slice tau, Wx tau was 0, right? Because, see, Wx tau is 0. For every tau it is 0. Because that is the 0 condition that you are giving. At every time slice it is 0. So, this fellow is 0 and you are only left with this. Okay. Now, you have got some integral of some quantity, and now you have to evaluate that fellow at time t is equal to 0. Now, because this t is equal to 0 now, that also doesn't contribute, so you get 0. So at least this candidate satisfies the two boundary conditions that you are after, that it is having displacement equal to 0 and also velocity equal to 0. Now only thing that is left to be shown is that this candidate actually solves the wave equation. Okay. So with the source term. Okay. Now, you see in the previous slide we showed that this is true, right? When I differentiate u with respect to t, I get this term. Now let us differentiate it one more time. One more time. When I differentiate this one more time, on the left hand side I get utt, and on the right hand side I do the same exact thing, the Leibniz integral rule. I get wt xtt plus one more term where you take the derivative inside. Now you see, this is where the magic happens, and that's why you are taking this fellow to be f of x comma t. In the equation for W, the boundary condition, the initial conditions were these, right? W x tau is 0 and Wt x tau is f of x tau. That was the boundary initial conditions for the problem. Now here you see you have this. Now that is actually equal to f of x comma t, because that's the condition here. And now W also solves the wave equation. So wherever you see Wtt, you can write Wxx at the same point. Now this is an integral with respect to the tau variable, and this is a derivation with respect to x variable. I can take this out. Okay. I will take the two derivatives out of the integral, and I am left with this integral. And we gave a name to this guy. We called this u, right? And you get this. So you see, this essentially tells you that this u solves utt equals to f plus uxx. That's the other way of saying that utt minus uxx is equal to f. Okay. So let's just go over this one more time, because this is the crucial step. Okay, so you got a candidate u of x comma t. So in Duhamel's principle, it's again a recipe for finding solutions to the wave equation when you've got a source term there. Okay. So you are defining u of xt is equal to integral from 0 to t of w x t tau d tau. Okay. Now we get this relation when I differentiate with respect to t. This is simply w x t t. I'm blindly using the Leibniz rule. Okay. I have to evaluate at this point and then multiply by the derivative of that, which is 1. Plus integral from 0 to t. The other term is when the derivative goes inside and hits the integrand, xt tau d tau. Okay. Now wxtt is 0, because that's how that is the initial conditions that we are giving. Wtt minus wxx is equal to 0. That's the equation solved by w. And wx tau is equal to 0, and wtx tau is equal to f of x tau. That is the initial value problem for w that we have. So this fellow will not contribute, and you are only left with this. Now when you differentiate again, okay, this should go now. See, in this step, we are just differentiating one more time. utt is equal to, now again you do the same exact thing. Wt, you evaluate when tau is equal to t. We are blindly applying the Leibniz rule. Plus integral from 0 to t, wtt xt tau d tau. Now we know what is wtxtt. Go back to this, it says f of x comma t. This is the step which gives you the source term. Okay? So this gives you f of x comma t. Plus, now what is wtt? It's equal to wxx. That's the equation satisfied by w. So I'll replace this wtt by wxx at the same point, xt tau d tau. Now this is a derivation with respect to x. This is an integration with respect to tau. So I can take the derivation outside. So this is, first term we are not touching. We are happy that we have got an f there. So this becomes d square x integral from 0 to t w x t tau d tau. But we gave a name to this guy. This is what we called as u of x comma t. And that is being differentiated twice in space. So you see, this recipe of Duhamel, it essentially tells you that if you are given a wave equation with a source term, you take that source term as your initial velocity, okay, in this auxiliary problem, in this separate problem. You have to solve this problem for every tau positive until the time t. And then you simply integrate that fellow from 0 to t in the tau variable. Okay? So here we have just given an example. So this is the auxiliary problem, the intermediate problem that you need to solve for w. And see, as I told you earlier, if I am given data on this line, on this red line, I can blindly use the Duhamel's formula to write down the solution, and that's what we will do now. In Duhamel's formula, there are two terms. There is one which is coming from u0 and one coming from u1, right? and u naught is 0 here. So that term is not there. So you have to simply integrate this fellow between these two guys. Because where are you standing? You are standing at the point x comma, suppose you are standing at the point x comma t. So suppose this is the point x comma t that you are standing. When I draw those lines of slope 1, and this is the t is equal to tau t, right? This x is equal to t line, it intersects this point at exactly that point, x plus t minus tau, okay? And x minus t minus tau, sorry. So this is x minus t minus tau, and the other one will be x plus t minus tau, okay? That's the, because t minus, here is t, and you already moved up by tau. So what is left is t minus tau, this length, okay? So x minus t minus tau, x plus t minus tau. So this you have to integrate your velocity, the data, because this is u1 is f here. u1 is f, you have to integrate that. And that you are integrating in the y variable. Because tau is fixed, you do this. And then you can, because now once you have got an equation for w, an expression for w, the recipe is you have to simply integrate from 0 to t the tau variable to get u. So you get u of xt as integration from 0 to t in the tau variable. So we have simply integrated this guy in the tau variable, and that half was there from the D'Alembert formula, it stays on. Now this may look ugly, so we make a change of variable. Okay, we call t minus tau as L, so somewhat simpler looking expression comes, but they are one and the same. You get this expression. So you see, the point I'm trying to make in this slide is that you are not solving a bunch of auxiliary problems all the time. That was just a principle. Now this is a formula. If somebody gives you a source term f, you simply compute this integral and that fellow is your solution. Okay, like if there is an initial value problem, okay, with zero data but only source term, we should not take Duhamel's principle as, okay, I have to solve a bunch of problems for W. That is done already here. So this is a recipe again. If somebody gives you a source term f, you blindly write down this, compute this expression, and that gives you the solution to the wave equation with that fellow as the source term. Okay? Now, in the last slide, okay, I promise you after that we take some tea. Now, you see, what are we doing here? We are interested in solving this problem. So, the most general initial boundary value problem will look like this, right? The most general initial boundary value problem for the wave equation will look like utt minus uxx is equal to some function of x and t. U of x comma 0 is some function of u naught, some function of x, and ut at x comma 0 is some function of u1, some function of x again. So there are no zero data here. It's like there is a source term, there are these initial values which are also given. Now, can we, how do we go about solving this? Okay, the recipe is here. What you do is, first you solve for this capital U with that fellow f as the source term, but zero initial data. Okay, we have got a recipe for writing down and what is the expression for capital U in terms of f from the previous slide, right? So, in the previous slide, we derived a formula. This is the formula. Like if somebody gives me a little f, this fellow is the solution to the wave equation with that as the source term with zero initial conditions. Okay. Now, it has got that structure. We have got an expression for capital U just in terms of f. Now you write down this fellow. This has got zero source term, but it has got initial conditions. In this case, we know how to write down the solution using D'Alembert formula, okay, which has got the average of u0 at certain points and u1 integrated in some interval. Then what you do is you simply add the two together. Okay, because of the superposition principle which I mentioned in the previous lecture, the sum will solve that problem. The sum of those two functions will solve this problem because this source term is coming from one of them, the initial data is coming from the other. Okay. So if you sum those two, you have actually solved this most general initial value problem with the source term. Okay. So some people use this terminology like non-homogeneous equations and all, but essentially it means that there is some f sitting there. Okay. And this is the formula. See, this fellow is the D'Alembert formula. This is the formula which involves the f, which we derived in the previous slide. So we have got a recipe again. Like if you give that general looking initial boundary value problem, sorry, there is no boundary here. Initial value problem with a source term. This is the fellow which solves that problem, and this is the unique solution. Okay. So once you are given an f, you simply compute this integral and D'Alembert's formula. You just add. Okay. So with this, I would like to stop here. Sorry, I took a lot of time. Yeah. So we'll take a break and then we'll try to solve some of the problems. Okay. Yes. Yes. Oh, there is another.
For online session, we are not